This is the first 9 weeks exam review sheet, the first half of the final exam review. Number 1 says particles in each state of matter are shown in the diagrams below: solid, liquid, gas. Label each arrow with the correct change of state name. When a solid changes into a liquid, it melts. When a liquid changes into a gas, it evaporates. When a gas changes back into a liquid, it condenses. And when liquid changes into a solid, it freezes. The next one, number 2, says fill in each blank below with definite, which means it won't change, or not definite, which means it will. A solid's shape and volume are both definite. They do not change. A liquid's shape is not definite. It takes the shape of its container. But its volume is definite. A gas's shape and volume are both not definite. A gas can move freely into any shape and amount of space it has. Number 3 says identify each of the following as either an element, compound, homogeneous mixture, or heterogeneous mixture. Ice is just water. We know that water is H2O. Those are both two different elements, and we know that two elements make a compound. Apple juice is a mixture, but it looks the same throughout. So even though it's a mixture, a combination of a bunch of things, it all looks like one. So that would be a homogeneous mixture. Sand is a heterogeneous mixture. And oxygen is on the periodic table, so that is an element. Number 4 says identify each of the compounded particles in each box as either an element, compound, or mixture. So if we look at letter A, we can tell that all of these are the same, but each one is made up of two different colors, so that would represent a compound. In box B, we can tell that these are both the same color, and these are both the same color. They are not attached together. They're not bonded. So this is one element. This is a different element. So because they're two different elements that are not attached, that's a mixture. Box C, we notice that every single one is the same. That represents an element. And in box D, we see that there are two combined together, but because they're the same color, that is still just an element. Box W is way over here. We can see that this is different from this, which is different from that, so that would be a mixture. Box X is similar to box C. Everyone is the same, so that is an element. Box Y, this is small and this is large, so this together are two different things. This is a compound. Each of these is the same, so this is just a compound. And then box Z, once again, this is the same as that. Each one is the same, but they are made up of three different elements, so that would also be a compound. Number 5 says how are the atoms in a pure substance combined compared to those in a mixture? Give an example from above. So a pure substance would be like box A or D. So if you look at these, right, they are attached. They're attached, right? So they are bonded together. In a mixture, they're not. So you can see how this is a compound that is bonded together, this is a compound that is bonded together, but they are mixed in the same space. So box W would be an example of a mixture. Number 6, how must the atoms in a pure substance be separated compared to the atoms in a mixture? So if they're bonded together, it will take a chemical reaction in order to separate them. For a mixture, we can just separate them by physical means. I can pick out the large pieces, I can filter, anything like that by physical means. Number 7 says place an X in the box that best describes each example below. There's only one X per row. So if H2 and O2 react to form water, that would be a chemical change because something's changing. Crumbling a sheet of paper, that would be a physical change. The paper is still the same, but I have now crumbled it up. Gold melting. If gold melts, that would also be a physical change. Remember, if you look back at the top, right? Melting is just changing from a solid to a liquid, so it would still be gold. That's a physical change. A battery will corrode. That's a chemical property. It will happen. It's not currently changing, so that's why we call it a chemical property. Burning a sheet of paper, it's a chemical change. It'll no longer be paper. H2O has a freezing point of 0 degrees Celsius. That's a physical property. Last one, number 8. Says list the 4 different sides that are evidence a chemical change has taken place. So those are an unexpected color change, an unexpected temperature change, like it gets hot or cold, light being produced, a precipitate, that's when I get a solid that forms at the bottom of my container. And last, the most common is bubbling, which is production of a gas. Okay, so that's the end of the front of this piece of paper. So if we turn it over and look at the back, there's some calculations. So number 9 says calculate the density of the 2 substances described, then identify whether each will float or sink in water. So remember, density equals mass divided by volume. So A, a 1.5 gram piece of styrofoam, has a volume of 10 milliliters. Will it sink or float? So density is mass. Mass is grams, so 1.5 grams divided by volume, which is 10 milliliters. 1.5 divided by 10 is 0.15 grams per milliliter. Remember, we can decide if it'll sink or float, whether the density is greater or less than 1. So if this is less than 1, it will float. A metal container has a mass of 25.5 grams, 20 milliliter volume. Same thing, density equals mass divided by volume, 25.5 grams over 20 milliliters. 25.5 divided by 20 is 1.275. This is now greater than 1, so this object will sink. Then letter C says if the metal container from part B was cut in half, how would its density change? And the answer is it would not. The reason for that, it says explain why, is because if I cut the piece of the metal container in half, the mass would get cut in half, but the volume would also get cut in half. So if I divided 25.5 in half, that would leave me a mass of 12.75. And if I cut my volume of 20 milliliters in half, that would be 10 milliliters, and I would still get the exact same density. Number 10 says convert the following numbers to or from scientific notation as appropriate. So we can see this number is already in scientific notation. So 1.3 times 10 to the 4th. That 4 means I move my decimal 4 times. It's positive, so that means this is a big number, and I should move my zeros to the end of the number. So I have 1, 1, 2, 3, 4, and you get 13,000. When there's a negative exponent, that means that this is a small number, and so I should move my decimal in the front of the number. So I start with 24, I move it 1, 2, 3, and I get 0.0024. Now when I have my number in standard notation and I want to move it, I can't see my decimal, but it's here at the end. I want to move it so that there is only one number in front of it, so I get 5.6 times 10, and then I moved it 3, 4, 5, 6 times. Positive 6 because this was a large number. So now I can see my decimal. I want to move it between the 7 and 8 so that there's only one non-zero number in front. So I get 7.8 times 10 to the 1, 2, 3, 4. Negative 5 because this is a small number. Number 11 says perform the following metric conversions. Metric conversions is where I use my dimensional analysis. So I start with 25 liters. I have liters. I no longer want liters, so I cancel it out on the bottom. I want to convert to milliliters. Then you use your conversion factor. You say 1 milliliter is equal to 1 times 10 to the negative 3 liters. And so you'll divide here. 25 divided by 1 times 10 to the negative 3, and you get 25,000 milliliters. For letter B, we start with 400 kilograms. I have kilograms. I no longer want kilograms, so those same units mass cancel out on the bottom. I want to convert this into grams. 1 kilogram, according to my conversion factors, is equal to 1 times 10 to the positive 3. This time I multiply. So 400 times 1 times 10 to the 3 gives me 400,000 grams. Now if you notice here I'm going from millimeters to centimeters. So now I know I need to use a two-step problem. So I start with 1.5 millimeters. I'm going to cancel out millimeters, but I cannot convert directly into centimeters. So I must go to meters first, cancel out my meters, and finally convert into centimeters. So 1 millimeter is 1 times 10 to the negative 3, and 1 centimeter is 1 times 10 to the negative 2. So at the top I multiply 1.5 times 1 times 10 to the negative 3, but then I'm also going to divide that by 1 times 10 to the negative 2. And my final answer is 0.15 centimeters. For letter D, I have centimeters to kilometers. That is also a two-step problem. Notice I'm starting with my number in scientific notation this time. That makes no difference. I just treat it like any other number. So 1.5 times 10 to the 10 centimeters. I cancel out centimeters. They both have meters. And then my second step is meters converting into kilometers. So 1 centimeter is 1 times 10 to the negative 2. 1 kilometer is 1 times 10 to the positive 3. So once again, I multiply 1.5 times 10 to the 10 times 1 times 10 to the negative 2, and then divided by 1 times 10 to the positive 3. Get 150,000 kilometers. Number 12 says to read the instruments to the proper number of significant figures. So remember, you can always estimate one digit past what you can see. So I can see that this is 2. So for letter A, this is 2.1. It's between 0.1 and 0.2, so I know 0.1 for sure. But now I'm going to estimate that it's pretty close to 2. So that's going to be like maybe 0.8. So 2.18. For letter B, I can see again that it's at least 2. But now it looks like it's exactly on 0.6. So I'm going to estimate that it's exactly on that 0.6 line by estimating a 0. And then for letter C, I can see now that it's past the 3. So now I have 3. It's not quite at 0.1, so that's a 0. And then I can estimate the amount that it is between here. It's closer to the 3, so maybe 0.03. These would be similar, so I can see that this is 20, 21, 22, 23, 24, 25. So it looks very close to 24. I can estimate that it's exactly on the 24 line by putting a 0 there, so degrees Celsius. This one I read the graduated cylinder using the bottom of the meniscus, and so I have 10, 11, 12, 13, 14, 15. Maybe it appears just above the 15 line, so I could estimate 15.1 milliliters. Isotopes. Number 13. For each of the isotopes, determine its missing information, then use the abundances given to calculate average atomic mass. So, you'll need your periodic table. If it says silver 107, this 107 is the mass number. That's what's given to you. You can look at the periodic table to find the atomic number of silver. That's 47. Remember, the atomic number tells us how many protons there are. In a neutral atom, the number of protons is equal to the number of electrons, and we can subtract the mass from the atomic number to find the neutrons. So 107 minus 47 equals 60. That's my number of neutrons. So my nuclear symbol would be the symbol for silver. The mass goes at the top, and the atomic number goes at the bottom. So then we can do the same thing here. We notice the same protons, right? So my atomic number must be the same. My electrons must be the same. But now notice I have one more neutron, so my mass number is now 108. So this must be silver 108. My nuclear symbol would still be silver, my mass would be 108, but my atomic number is the same, 47. So remember, we calculate average atomic mass by using the percent abundance and the mass number. Percent abundance and the mass number. So we multiply and then add them together. So 107 times my percentage, don't forget to move your decimal, 2 times to the left, so 0.5186. So you'll do that, and then you'll add to that 108 times, and I'll move my decimal 2 times, 0.4814. So multiply, add those together, and you should get something, let's see. 108. Remember to do them separately or use parentheses in your calculator. Let's see. 107 times 0.5186, and then separately or in parentheses 108 times 0.4814, and we add those two together. You get something like 107.48. And so you notice my answer should be between my two masses because I'm taking the average atomic mass of them. So you try this next one and you can see your teacher if you would like to check your answer. Notice this is going to be silicon 28, this will be 30, and your average should be somewhere in between them, probably closer to 28 because it has quite a high percent abundance. The last question says to draw the Bohr models for the following elements. So for helium, remember we look at the periodic table. Protons is given to us by the atomic number, so there's 2 protons. Neutrons we can determine by subtracting 4 minus 2 is also 2, and my electrons to match my protons, so 1, 2. My first energy level holds 2, so that's all I need. For carbon, I look at the periodic table. My protons are 6 because the atomic number is 6. I calculate neutrons by subtracting 14 minus 6 is 8, and my electrons should match my protons, 6. So 2 go on the first energy level. After that I need another energy level, 1, 2, 3, 4. And then last for argon, you find the atomic number on the periodic table, so that would be 18. You find the neutrons by subtracting 40 minus 18, 22 neutrons. My electrons must cancel out my protons, so I have 18. 2 on the first energy level, 8 more on the second energy level. It's a total of 10 so far. And then we need one last energy level for the remaining 8. Okay? So just go back and try that one. Get your answer from your teacher. And that's it.